Right now, somewhere in a windowless office at the Pentagon, a small team of analysts is opening a folder containing a video the Department of Defense cannot explain. Not because it involves anything otherworldly, but because the object in the footage moved in a way that does not match any known aircraft, any known weather phenomenon, or any known optical illusion, and nobody on that team is willing to close the file until they genuinely understand why. At the same time, in university physics departments scattered across the world, researchers who spend their careers thinking seriously about the odds of life beyond Earth are becoming increasingly convinced that the universe should already be full of noise, full of signals, full of evidence, and it is not. And it started, of all places, over lunch at a national laboratory built to design nuclear weapons, where one physicist's offhand question turned an idle conversation about flying saucers into one of the most enduring open problems in the history of science. Two entirely different groups of serious, credentialed people are staring at the same underlying question from opposite directions, and neither one has an answer that fully satisfies the other. This is the actual state of the science around unidentified objects and the search for life beyond our planet in 2026. And it is far stranger, far more carefully argued, and far less settled than either the confident skeptics or the confident believers online would ever have you think. Stay with me, because by the end of this, you're going to understand exactly why physicists keep saying the silence out there is getting harder to explain, not easier, and why the government's own investigators keep saying the same thing about the sky above our heads. If careful, evidence-based explanations of genuinely open scientific questions are what you come here for, go ahead and subscribe now. Because this is one of the few mysteries in modern science that experts on every side, government investigators, astrobiologists, and theoretical physicists alike, all agree is still genuinely wide open. Let's start with where this entire question actually began, because the origin of it is almost as famous in physics circles as the question itself. In the summer of 1950, the Italian physicist Enrico Fermi, one of the towering figures behind the development of nuclear physics, was having lunch with several colleagues at Los Alamos National Laboratory. The conversation had drifted toward flying saucers, a subject very much in the news at the time, and then toward the broader question of extraterrestrial civilizations. According to the people who were there, Fermi went quiet for a while, apparently doing rough calculations in his head, and then asked a simple question that nobody at the table could answer. Where is everybody? It sounds almost too casual to be the foundation of a serious scientific problem, but the reasoning underneath it is genuinely rigorous. The Milky Way galaxy contains somewhere between 100 billion and 400 billion stars. Even using conservative estimates about how many of those stars might host planets capable of supporting life, and how often life might evolve into an intelligent, technological civilization, the numbers suggest that even a modest handful of successful civilizations, spreading outward using nothing more advanced than slow, sublight speed spacecraft, could colonize an entire galaxy the size of ours within a few tens of millions of years. That sounds like an enormous span of time from a human perspective, but the galaxy itself is roughly 13 billion years old. A few tens of millions of years is a rounding error on that scale, a blink relative to the deep history of the Milky Way. Which means that if intelligent life is even moderately common, someone should have already gotten here. Or at the very least, we should be able to see clear evidence of their presence somewhere out there. And we do not. That gap between what the math suggests should be true and what we actually observe is the Fermi paradox, and more than 70 years later, it remains one of the most stubborn open questions connecting physics, biology, and philosophy. To understand why this question refuses to go away, it helps to walk through the tool scientists actually use to think about it formally, a framework called the Drake equation, developed by the astronomer Frank Drake in 1961. It is not really an equation in the sense of producing a single confident number. It is closer to a structured way of breaking an impossibly large question into smaller, more manageable pieces. It asks you to estimate the rate of star formation in the galaxy, the fraction of those stars that have planets, the fraction of those planets that could support life, the fraction of those that actually develop life, the fraction of that life that becomes intelligent, the fraction of intelligent life that develops technology capable of sending detectable signals into space, and finally, how long such a civilization might survive and keep broadcasting before it either destroys itself or simply falls silent. Multiply all of those fractions together, and you get an estimate for how many technological civilizations might currently exist in our galaxy at the same time as us. The problem, and the reason this equation has generated genuine scientific arguments for over 60 years, is that almost every single term in it remains deeply uncertain. We now actually have solid data on some of them, thanks largely to the Kepler Space Telescope and its successors, including the ongoing work of ground and space-based surveys still active today. Astronomers have confirmed more than 5,800 exoplanets as of this year, with thousands more candidates awaiting confirmation, and the data consistently suggests that planets are not rare at all. Most stars appear to host at least one planet, and a meaningful fraction of those sit within the so-called habitable zone, the region around a star where temperatures could allow liquid water to exist on a rocky surface, neither so close that oceans boil away, nor so far that they freeze permanently solid. That term in the equation, once treated as a wild guess based on nothing more than intuition, is now grounded in genuine observational data gathered across 2 decades of dedicated survey work, and it points toward potentially billions of candidate worlds in our galaxy alone, a number that would have sounded like pure fantasy to the scientists debating this question only a generation ago. But the terms that come after that, the fraction of habitable planets where life actually emerges, and the fraction of that life that becomes intelligent and technological, remain almost entirely unconstrained by any real data, because we still only have exactly one confirmed example of a planet with life on it, the one we're standing on right now. Trying to estimate the probability of something happening when your entire sample size is one is a genuinely difficult statistical problem, and it is the single biggest reason serious researchers can plug wildly different numbers into the Drake equation and walk away with estimates for the number of civilizations in our galaxy ranging from essentially 0 to literally millions, all while using scientifically defensible assumptions. That range alone tells you something important. The Fermi paradox is not a fringe question asked by conspiracy theorists. It is a legitimate, unresolved tension sitting at the intersection of astronomy, biology, and probability theory, debated by working physicists in peer-reviewed journals, not internet forums. If you have found this framing more useful than the version of this debate you usually see online, take a moment to hit the like on this video right now, because it genuinely helps careful explanations of open scientific questions reach more people than the confident, oversimplified versions competing for the same attention. Over the decades, researchers have proposed dozens of possible resolutions to the paradox, and it is worth walking through the major categories, because each one carries real scientific weight and each one has real problems. One family of explanations is often called the rare Earth hypothesis. The idea that while simple microbial life might actually be common throughout the universe, the specific combination of conditions required for complex, intelligent life is extraordinarily rare. Earth benefits from an unusually large moon, formed billions of years ago in a collision between the young Earth and a Mars-sized object that stabilizes its axial tilt and keeps our seasons predictable over geological timescales. It has a molten iron core that generates a protective magnetic field, shielding the surface from the kind of relentless solar and cosmic radiation that has apparently stripped away the atmosphere of a planet like Mars over billions of years. It sits in a fortunate position within the galaxy, far enough from the dense radiation-heavy galactic center to avoid the kind of sterilizing events that could wipe out surface life entirely, yet close enough to have access to the heavier elements needed to build rocky planets and complex chemistry in the first place. And it has enjoyed a long, geologically stable history, largely free of the kind of catastrophic asteroid impacts or nearby supernova explosions that could reset the evolutionary clock back to nothing. If all of those specific factors, the moon, the magnetic field, the galactic location, the geological stability, need to align simultaneously and persist for billions of years, then complex life, let alone technological civilization, might genuinely be an astronomically rare event, even on a galactic scale with hundreds of billions of stars to draw from. A second major family of explanations is called the Great Filter, a concept introduced by the economist Robin Hanson in the 1990s, and still actively debated by astrobiologists today. The idea is that somewhere along the evolutionary path from simple chemistry to a civilization capable of colonizing other star systems, there exists at least one extraordinarily difficult transition, a filter that almost nothing manages to pass through. The genuinely unsettling part of this idea is that we do not know whether humanity has already passed that filter or whether it still lies ahead of us. If the filter is behind us, something like the origin of life itself, a chemical transition scientists still cannot fully reproduce in a laboratory despite decades of dedicated effort, or the jump from simple single-celled organisms to complex multicellular life, a transition that took roughly 2 billion years on Earth after life first appeared, an almost unimaginably long stretch of evolutionary stagnation. Then we may be one of the rare, fortunate civilizations that made it through, and the universe's silence is simply the sound of countless other worlds that never got that far. Worlds still sitting quietly at the level of simple bacteria, with no path forward toward anything more complex. But if the filter still lies ahead of us, in the form of nuclear war, engineered pandemics, uncontrolled artificial intelligence, catastrophic climate collapse, or some other self-inflicted disaster that reliably ends technological civilizations shortly after they develop the capacity to broadcast their existence into space, Then the silence takes on a much darker implication, one that Hansen and many researchers after him have taken seriously enough to write extensively about, and one that arguably carries real stakes for how our own civilization chooses to manage its own most dangerous technologies going forward. A third category involves what is sometimes called the zoo hypothesis, or various forms of the interstellar quarantine idea, the notion that advanced civilizations exist and are aware of us, but have deliberately chosen not to make contact, whether out of caution, ethical restraint, or simple disinterest in a civilization as young and unstable as ours, not unlike the way a wildlife researcher might observe an isolated tribe from a careful distance without ever revealing their presence. Most working physicists treat this explanation with real skepticism, not because it is impossible, but because it requires assuming a remarkably uniform, coordinated behavior across every single advanced civilization that might exist, an assumption that becomes statistically less plausible the more potential civilizations you imagine existing. It only takes one curious, expansionist civilization out of potentially millions to break the silence, and the fact that we have never detected one suggests either that such civilizations are far rarer than optimists assume, or that something else entirely is going on. And then there is a newer explanation that gained real traction over the last decade, sometimes called the Great Silence Hypothesis, or the digital transcendence idea, the suggestion that sufficiently advanced civilizations eventually turn inward, building simulated or virtual environments so compelling that physical expansion into the harsh, resource-poor emptiness of interstellar space simply stops being worth the effort. Civilizations, in this framing, do not disappear. They just stop bothering to leave home, choosing instead to explore inner space rather than outer space. This is where the story takes its most recent and genuinely significant turn, because in August of this year, a new piece of research directly challenged that entire line of reasoning, and the physicist Sabine Hossenfelder, whose YouTube channel has become one of the most widely followed sources of serious physics explanation online, walked through exactly why the argument does not hold up the way many people assumed it did. The researcher behind this new analysis pointed out something that, once you hear it stated plainly, feels almost obvious in retrospect. The digital transcendence argument assumes that advanced artificial intelligence would make civilizations less interested in space exploration, content to stay home and explore virtual worlds instead. But the new analysis argues that this reasoning has the direction backwards. Advanced artificial intelligence, cheap autonomous robotics, and inexpensive mass-producible probes do not make space exploration less appealing. They make it dramatically easier. A civilization does not need to send fragile biological astronauts across interstellar distances at enormous cost and enormous risk in order to expand. It simply needs to send self-replicating or semi-autonomous machines capable of surviving the journey, gathering resources at the destination, and building more of themselves once they arrive. A concept physicists sometimes refer to as von Neumann probes, after the mathematician John von Neumann, who first worked out the theoretical framework for self-replicating machines back in the 1940s, decades before anyone seriously considered applying the idea to interstellar exploration. Such a probe would not need to carry food, water, breathable air, or any of the enormous life support infrastructure a crewed mission would require. It would not need to worry about the psychological toll of a multi-generational voyage, or the ethical questions raised by sending human beings on a one-way trip that might last centuries. It would simply need enough onboard intelligence to navigate, land, mine local materials, and construct copies of itself before sending the next generation onward to the next star system, a process that, once started, could in principle spread across an entire galaxy in a geological blink of an eye compared to the galaxy's actual age. If artificial intelligence makes this kind of expansion cheaper, safer, and more efficient rather than less appealing, then the explanation that civilizations simply lose interest in space travel once they develop advanced AI does not actually solve the Fermi paradox at all. It makes the paradox worse because it removes one of the more comfortable, frequently cited explanations for the silence, leaving fewer plausible reasons on the table for why an expanding galaxy full of intelligent machines would have somehow never reached us, or left any detectable trace of having tried. This matters because it reflects something important about how this entire field of research actually works, in contrast to how it often gets portrayed. Every few months, a new paper proposes a fresh explanation for the silence, and every few months, other researchers pick that explanation apart, testing its assumptions, checking its math, and either strengthening it or discarding it. This is not a field where speculation goes unchecked. It is a field where speculation gets rigorously argued over in the same way any other branch of theoretical physics gets argued over, precisely because the stakes of getting the answer right, or even getting closer to it, are so significant. Now, let's turn to the other half of this story, the part that dominates headlines far more than academic papers about probes and filters ever do. The question of what governments actually know about unidentified objects in our own skies. This is where the conversation tends to split sharply between two camps, and it is worth walking through what has actually been confirmed, on the record, by official investigators, because the real story is considerably more nuanced than either extreme version circulating online. In 2017, the Department of Defense declassified a set of cockpit videos captured by Navy pilots, showing objects moving in ways that defied simple explanation, accelerating and maneuvering in patterns that did not obviously match the performance envelope of any known aircraft. Those videos, given informal names like Gimbal and Go Fast by the online communities who studied them intensely, became the spark for a renewed wave of serious government interest in what officials now formally call unidentified anomalous phenomena, or UAP, deliberately moving away from the more culturally loaded term UFO. In response to mounting congressional pressure, the Department of Defense established the All-Domain Anomaly Resolution Office, commonly known as ARO, tasked specifically with investigating these reports using rigorous scientific and intelligence methodology rather than speculation. In March of 2024, ARO released the first volume of a historical review examining decades of UAP-related claims dating back to 1945, combing through both classified and unclassified government documents, while also directly interviewing more than 30 people connected to various historical sightings and rumored programs. Its conclusions were direct. The office stated plainly that it had found no evidence that any UAP sighting represented extraterrestrial technology, and that all investigative efforts, across every level of classification, concluded that the vast majority of sightings were ordinary objects and phenomena, misidentified due to a combination of unusual lighting conditions, sensor artifacts, weather balloons, drones, and conventional aircraft, observed under unfamiliar circumstances. The report went further, actively debunking several specific, long-circulating claims by name, including a former military officer who had publicly claimed to have physically touched an extraterrestrial craft, a claim ARO traced back to what was actually an F-117 Nighthawk stealth fighter jet, a highly classified aircraft at the time that would have looked genuinely alien to someone without proper clearance. The report also directly addressed persistent claims that the government or private companies were secretly reverse engineering crashed extraterrestrial technology, stating clearly that no empirical evidence supported those claims either, and that individuals who had mistakenly connected authentic, sensitive national security programs to UAP activity had generally done so based on incomplete or unauthorized access to fragments of classified information, pieced together in ways that created a misleading picture. That should, in theory, have settled the matter entirely, but it did not. And the reason it did not is itself an important part of the story worth understanding. Throughout 2024 and into 2025, congressional hearings continued, featuring testimony from former officials, including one named Luis Elizondo, who publicly claimed the government had conducted secret UAP crash retrieval programs and was actively concealing evidence of non-human technology from the public and from Congress itself. Despite the seriousness with which these hearings were conducted, and despite extensive follow-up investigation, no verifiable physical evidence supporting those claims has ever been produced. John Kozlowski, the director of ARO, has repeated the same conclusion in multiple public statements since taking the role, that the office continues to receive hundreds of new reports every year, that a meaningful fraction of those reports remain genuinely unresolved even after thorough investigation, but that unresolved does not mean unexplainable, and it certainly does not mean extraterrestrial. It typically means the available sensor data was simply not detailed enough to pin down a conventional explanation with full confidence. That distinction between unresolved and unexplainable is precisely the space where honest scientific uncertainty and public speculation tend to diverge sharply, and it remains just as relevant in 2026 as it was when ARO first published its findings back in 2024. Just this past July, the Pentagon confirmed it was actively investigating a new UAP event reported by Navy personnel off the coast of Virginia, and earlier this month, the Department of Defense released its fifth batch of declassified UAP files, including sensor footage showing objects described as cold orbs maneuvering aggressively at altitudes between 250 and 1,300 miles per hour, footage that, according to the accompanying report, remains formally unresolved alongside additional clips submitted by military commands overseas showing similarly unexplained objects captured during routine operations. It is worth being precise about what unresolved actually means in this context, because the word gets stretched in both directions by people with opposing agendas. It does not mean the government has secretly identified the objects and is hiding the answer. It means that after running the available data through every conventional explanation, investigators could test sensor error, atmospheric distortion, drone activity, foreign surveillance technology. They simply could not reach a confident conclusion with the evidence on hand, and they said so publicly rather than manufacturing a tidy explanation just to close the file. This is also where the perspective of working physicists like Sabine Hossenfelder becomes genuinely useful. because it offers a different kind of scrutiny than either government investigators or online enthusiasts typically bring to the table. Physicists trained in general relativity and quantum field theory tend to approach dramatic UAP footage with a very specific and very demanding kind of skepticism, not because they assume the pilots reporting these sightings are lying or mistaken about what they saw, but because the physical requirements for genuine interstellar travel are so extraordinarily difficult to satisfy that any claim of an actual alien craft operating in our atmosphere needs to clear an extremely high bar of evidence before it becomes the most probable explanation. The nearest star system to our own, Alpha Centauri, sits more than 4 light-years away, a distance so vast that even our fastest current spacecraft would take tens of thousands of years to cross it. Bridging that gap in any reasonable amount of time would require either technology capable of approaching the speed of light, which brings with it a genuinely enormous energy cost that scales dramatically as you approach that limit, since the amount of energy required to accelerate any object with mass grows toward infinity. The closer it gets to light speed, or some form of exotic physics, like the theoretical Alcubierre warp drive, a real mathematical solution within general relativity, first proposed by the physicist Miguel Alcubierre in 1994, that would technically allow a ship to travel faster than light relative to distant observers by contracting space in front of it and expanding space behind it, without the ship itself ever locally exceeding the speed of light. The catch, and it is a significant one, is that this solution requires negative energy density, a form of matter with genuinely bizarre properties that has never been experimentally confirmed to exist in any usable quantity, only in tiny, fleeting amounts under very specific laboratory conditions involving quantum effects, nowhere close to what would be needed to warp space around an actual vehicle. None of that rules out the theoretical possibility of advanced propulsion methods we simply have not discovered yet, and serious physicists genuinely keep an open mind about that possibility. But it does mean that when a blurry cockpit video shows an object moving in a way that looks strange to a human pilot working under stressful, fast-moving conditions with limited sensor context, the vastly more probable explanation, based purely on the physics and the base rate of misidentification across decades of aviation history, is a mundane one involving sensor artifacts, parallax effects, or conventional technology, rather than a craft that somehow solved one of the hardest unsolved problems in theoretical physics, and then decided to fly erratically over a military exercise. That is not the same as saying nothing strange is happening. It is saying that extraordinary claims require correspondingly extraordinary evidence, a principle sometimes summarized by the phrase Carl Sagan popularized decades ago, and that principle cuts in a specific, consistent direction. A blurry video showing an object moving unusually is genuinely interesting and absolutely worth investigating seriously, which is exactly what Arrow continues to do. But it does not, on its own, meet the bar required to conclude that the object is evidence of a civilization that has solved interstellar travel, especially when the same physics that makes interstellar travel so difficult also applies, in principle, to any civilization capable of attempting it in the first place. If advanced beings really were crossing light years of empty space to visit a mid-sized planet orbiting an unremarkable star, the sheer scale of engineering required to accomplish that journey should, in theory, leave behind detectable evidence far more definitive than a grainy heat signature video, evidence like unambiguous radio transmissions, unmistakable propulsion signatures, or physical material with an isotopic composition that could not have originated anywhere in our own solar system. So far, across every serious investigation conducted by ARO, by independent academic researchers, and by dedicated technosignature searches using instruments built specifically to detect artificial signals from space, none of that harder evidence has ever been confirmed. This is precisely where the two threads of this story, the Fermi paradox and the UAP investigations, actually connect, and it is a connection worth sitting with for a moment, because it reframes the entire question in a more interesting way than either topic manages on its own. If advanced alien civilizations were regularly visiting Earth, flying craft in and out of our atmosphere with enough frequency to generate the hundreds of UAP reports ARO receives every year, that would actually resolve the Fermi paradox rather elegantly. It would mean the silence was never real in the first place, that we simply had not been looking in the right place, or had been unwilling to accept the evidence sitting in front of us. But the overwhelming consensus among physicists working directly on the Fermi paradox is that this explanation does not fit the broader pattern of evidence nearly as well as it might initially seem. If a civilization possessed the staggering technological capability required to cross interstellar distances routinely enough to explain the volume of UAP sightings, that same civilization should, almost certainly, also be detectable through countless other channels. Unmistakable energy signatures, structured radio emissions, or observable engineering on a stellar scale, none of which any telescope, radio array, or space-based observatory has ever confirmed. The silence that troubled Fermi in 1950 remains, on the whole, still profoundly silent. And a scattering of unresolved cockpit videos, while genuinely worth investigating, has not meaningfully changed that broader picture. So where does that leave us, sitting here in 2026, with more confirmed exoplanets than ever before, a newly operational generation of observatories specifically designed to characterize the atmospheres of distant worlds for signs of biological activity, and a Pentagon office that keeps receiving reports it cannot fully explain? The honest answer, the one that most careful physicists working on this question would actually give you, is that we do not know, and that not knowing is not a failure of science. It is precisely the kind of genuine, productive uncertainty that drives science forward. The universe has not handed us either a confirmed alien visitor or an explanation for why civilizations should be common and yet completely undetectable. What it has handed us is a slowly accumulating pile of better instruments, better statistics, and better arguments, each one narrowing the range of plausible explanations just a little further than the last, without yet closing the gap entirely. Every new exoplanet discovered by observatories now scanning the sky pushes the terms of the Drake equation a little closer to being grounded in real data rather than pure speculation. Every UAP report that AARO investigates and either resolves or honestly labels as unresolved adds one more data point to a growing, transparent, publicly available record rather than a sealed file locked away from scrutiny. And every new theoretical paper, like the one that argued advanced artificial intelligence should make interstellar expansion easier rather than less appealing, forces the entire scientific community to sharpen its reasoning just a little further, discarding weaker explanations and holding on to the ones that can actually survive rigorous argument. That is the real, unglamorous, and genuinely fascinating state of this question right now. Not a hidden truth being suppressed by shadowy officials, and not a confident dismissal from scientists who have already made up their minds. It is an open, actively contested scientific problem, argued over in peer-reviewed journals and congressional hearing rooms alike, with serious people on every side still working, in public, using published data and citable sources rather than anonymous claims, to figure out where the evidence actually points. The silence Fermi noticed over lunch in 1950 is still there, 76 years later, just as loud, just as strange, and just as unresolved as it was the day he first asked the question. If you want to understand where this goes next, whether it is the next exoplanet atmosphere read by our most advanced telescopes, or the next declassified batch of files from the Pentagon, subscribe and turn on notifications, because this is exactly the kind of question worth tracking carefully, rather than settling for whichever answer feels most satisfying in the moment. Share this with someone who has strong opinions on either side of this debate, because the most useful thing anyone can bring to a question this genuinely open is not more certainty, but more patience for the evidence to actually arrive.